My name is Lala Abdelhadi and I'm going to talk about optical and electrical characterization of organic solar cells using gold and silver metal nanoparticles. What is an organic solar cell? An organic solar cell or a plastic solar cell is a polymer solar cell that is a type of photovoltaic. Photovoltaic means the generation of voltage and electric current in a material upon exposure of light. And this cell uses organic electronics, which is a branch of electronics that deals with conductive organic polymers or small organic molecules for light absorption. Let's talk about the advantages of organic solar cells. First, it's low production cost. Second, processing at room temperature, so it doesn't need complicated conditions to operate. Third, mechanical flexibility. As we saw in the previous pictures, it can bend in different shapes. However, low efficiency and stability are the problems of organic solar cells. We tend to solve these problems using metallic nanoparticles. Doping techniques are used for gold and silver nanoparticles to put them on the surface of the organic solar cell. The difference in size and variety of nanoparticles play an important role in trapping the light. So, when the light is sent to the metallic nanoparticles, the energy of the light is stored in the vibration mode of the nanoparticle as a result of scattering and absorption of the light. So, this will improve the efficiency of the device. For experimental procedure, we will see how to synthesize Ag and Au nanoparticles and how to prepare the solar cells. For the synthesis of Ag nanoparticles, chemicals is mixed and stirred at 700 rounds per minute under continuous nitrogen flowing. Then, this mixture is heated up to 60 Celsius slowly and kept at this temperature for 5 minutes. Next, the resultant mixture heated to 180 Celsius and kept at this temperature for 20 minutes. After that, solution is cooled down to 40 Celsius and this mixture is centrifuged for 15 minutes after adding isopropanol. Then the nanoparticles were separated in the centrifuge tube, so Ag nanoparticles will be obtained finally. For Au nanoparticles, we will have a chemical mixture that will give us monodisperse Au nanoparticle. In the next stage, the temperature of solution is adjusted to 4 to 5 Celsius with the aid of an ice bath and stirred for 2 hours. Then the solution is centrifuged after the addition of acetone and ethanol, then Ag nanoparticles is obtained. If we now look together at the first figure, we can see the composition of a solar cell. The first layer is a flexible transparent substrate that is represented by glass to allow light passage. ITO layer is a conductive oxide that represents the anode. The next two layers is the photoactive layers. Then lithium fluoride works as electron transfer layer. The aluminum works as the cathode. In figure 2, we can see the scanning electron microscopy images for the solar cell surface. In figure A, there is no Au or Ag added. B and C, we have added Ag and Au nanoparticles, and they are homogeneously distributed to achieve high-performing devices. The first result we got shows the relation between the light absorption and the wavelength. We can see that the optical absorption increased with the addition of Au and Ag nanoparticles at 500 nanometer wavelength. The increase in absorption could be related to the roughness that may scatter the incoming light, that lead to increasing the path length in the active layer. This figure shows the XDR patterns that provide insight into the atomic distribution in the unit cell in the ITO layer. The existence of Ag and Au nanoparticles are confirmed by the peaks observed at 38 and 26.5 degrees. The addition of Au and Ag seemed to enhance the solar cell crystallinity, as evidenced in the result, and this led to increased optical absorption of the devices. This result is obtained by making the atomic force microscopy analysis to investigate the surface roughness of gold and silver nanoparticles. Figure A shows that the surface roughness was not observed where no particles is added, while in Figure B indicates that Ag nanoparticles in the surface caused surface roughness and has many agglomerates. Figure C shows that Au on the surface caused very little roughness and agglomerates. The roughness increased with increasing amount of Au and Ag in the active layer. Also, high roughness may contribute to an increase in absorption due to increased light scattering in the active layer. This table shows the basic characteristic parameters of organic solar cells. According to our results, the open circuit voltage in fourth column and power conversion efficiency (PCE) of the organic cells have increased after Au nanoparticles and Ag nanoparticles doping. It increased from 2.11% to 2.55% after doping Au nanoparticles and from 2.11 to 2.23% after doping Ag nanoparticles in our organic solar cell configuration. Au nanoparticles and Ag nanoparticles may have a role such they act as a light scattering centers, so they might increase the distance which the light travels through the active layer, and as a result of this, the efficiency of solar cells increase. In conclusion, in this study we have investigated the effect of Au and Ag nanoparticles on organic solar cells. We show that the influence of metal nanoparticles on organic solar cell is positive effect results. It was also observed that Au and Ag nanoparticle enhanced the light trapping capability, charge transport properties, and optical absorption. The experimental results showed that the power efficiency and open circuit voltage of the organic solar cell increased after doping of Au and Ag nanoparticles. As a result, the doping of Au and Ag nanoparticles in active layers changed electrical parameters of the solar cells in a very efficient way.